Thank you. Start again. Yeah. Okay, so let's continue with the series of short lectures on black hole gastrophysics. And yesterday we started talking about the physics of accretion flows around compact, around particularly black holes. We learned what happens when you feed the black hole. And today we will continue from the point where we stopped the lecture yesterday. These are the main physical parameters that we are working with, okay? It is the theorist's dream to be able to compute every possible property of the system from only these three numbers: the mass of the black hole, the spin of the black hole, and the field supply quantified by the mass accretion rate. So I would like to stress the important point that angular momentum removal is absolutely crucial to understand the accretion onto black holes, the viscosity, okay, the effective viscosity of these disks is a very important thing that we need to be able to model in some way, okay. Simple reason, okay, so without angular momentum removal, if you had a particle orbiting at some radius, let's say, so imagine you have your central object here, and you have a particle in a circular orbit far away, tracing out the dashed red line, okay? So if there is no angular momentum removal, if there is no process that will remove the angular momentum of this orbit, the particle will never fall. It will never drift towards the central object, okay? Particles will forever stay in their orbits, and the radial velocity will be zero without some process for angular momentum removal, okay? If you have some process of angular momentum removal, if you have, in other words, some viscosity, you generate thermal energy from the system, okay? So you need, if there is no energy dissipation, no viscosity, there will be no radiation from the system. And if this was true, this would be in conflict with the observations of several systems. Okay, so there must be some process removing angular momentum from the system. You have any question? Oh. So the point here, which is a simple point, is that accretion flows, they are fundamentally dissipative systems, okay? They are dissipating energy. You need a process to remove the orbital energy. Otherwise, this will be in conflict. If there is no such process, this is in conflict with observations of several systems, such as quasars, as compact objects in binary systems in our galaxy. So therefore, we now need to understand, we need to talk a little bit about hydrodynamics and turbulence when we talk about black hole accretion disks. And so I thought it would be important to at least talk for a few minutes, giving a primer on fluid dynamics, okay? What are the main equations that you need to model such a system, a black hole accretion disk? You need the equations, the conservation equations of fluid dynamics. And in order to derive these equations, okay, hola. So in order to really understand what's going on around a black hole, you need to, at some point, you can't do only with gravity. You need fluid dynamics. So here I will now go through the equations of hydrodynamics. In fact, you need the equations of, you need to combine the equations with Maxwell equations to have a more complete thermodynamic of the system. But for now, let's forget about magnetic fields, and let's talk about the fluid dynamics. And I will show you the reasoning behind deriving the equations that describe a fluid in fluid dynamics, okay? So the idea is simple, okay? How do you describe a fluid which is evolving, which is dynamically evolving, and it's flowing, and it's happening interesting things with the fluid? How do you do it? So let's imagine here that you have some flow of some material, let's say water, oil, ionized gas, the gravitational potential of a black hole, the blood in your vessels, any fluid that you might think of. And let's consider here some part, a small part of this fluid, okay? Let's, for the purposes of this lecture, consider a little tiny cube describing some portion of this fluid, okay? So let's imagine that here at this particular spot, the density of the fluid we quantify by rho. We are considering some element of the fluid with some volume V, okay? And this the surface area of this fluid element is A, okay? And we define a vector which is perpendicular to the surface, to the surfaces that we are considering. So we have an unit vector here which is perpendicular to the faces of this fluid element, okay? And we define a vector as is common, an area vector, let's say, which is this unit vector times the element of area that we are considering, okay? All right, so we define now this element here. It's a fixed volume, okay, so let's not touch on let's not make this volume change with time, okay, for simplicity. Okay, so now what is the mass? What is the mass inside this fluid element, okay? What is the mass? Right, so the mass, how do we compute the mass inside this fluid element? We integrate rho over the volume of this fluid element, and we have the mass inside this element, this volume element, right? Okay, so this is the way that you derive, this is the basic reasoning through which you derive every possible fluid dynamics conservation, different versions of this reasoning. We ask ourselves, what is the rate of change of some quantity that we are using to characterize this fluid, okay? We ask ourselves, what is the rate of change of a fluid? In this case, what is the rate of change of the mass inside this fluid element? Okay, we ask ourselves, is there something happening? Is there, if you are considering a fixed volume, you have some flow passing through this fluid, this volume element, okay? So this is a part of the reason why you could think that the mass inside this element is changing, okay? Okay, so the rate of change of the mass of this fluid element is simply, you can write in this very simple way. Okay, that's easy to understand. This is the rate of change of the mass inside this fluid element. And I think it's easy to visualize that if the mass inside this fluid element is changing, that's because there is mass flowing through the surface of this fluid element, right? If there is mass flowing through the surface of this fluid element, If there is mass leaving through the surface, the mass inside the fluid element will decrease. Okay, that's so simple that it sounds a bit ridiculous to state this simple fact. Okay, so this quantity, the rate of change of the mass of the fluid, it must be equal to the net flow of mass across the surface. And this net flow of mass across the surface, let's call it a mass flow, a mass flux, sorry, phi. And how do we compute the mass flow across the surface in this fluid element? If you want, you can use a dimensional analysis to convince yourself that the mass flow you can characterize as the density times the velocity. So this is the mass flow vector, which is phi. And if we want the net flow of mass across the surface, we need to integrate this little guy here, this vector field. We need to integrate it across the area of the fluid element. Okay. So this is a basic statement. I am here stating the conservation of mass of the fluid element. Okay, the rate of change of the mass is equal to the net flow of mass across the surface. Okay, so far so good. So we write this with an integral form of this is an integral form of the conservation of mass. Now the next step here is to remember the divergence theorem. Remembering the divergence theorem that we all learned in the second year or even earlier of college. The divergence theorem states that if you integrate the divergence of a vector field across some volume, okay, that's equal to the integral of the flow of the flux of this vector field across the surface. Okay, very simple divergence theorem. Okay, and now we use this and we express the right side of this equation, the mass flow, in a slightly different way. We can now write the mass flow as, okay, divergence theorem. So now we have this. Okay, so far so good. And finally, we take the statement of the conservation of mass. We equal this to this. Now we have this very powerful statement about the conservation of mass in the fluid element, which we slightly will rewrite as this. Okay, we slightly rewrite this equation as this, which I will call it equation 4. And in order for this integral to be true, this must be the integrand must be equal to 0. And we end up finding finally the differential version of the conservation of mass for the fluid, which we call continuity equation. A very important equation, the first conservation equation in fluid dynamics. Ah, yeah. Okay, so this is the sign is wrong here. In order for this to make sense, because of the way I put the orientation of my unit vector, okay, If the mass decreases, you need to put a minus here, okay? You need to put, yes, you need to put a minus here in order for things to make sense. In other words, if this mass flow has if this mass flow vector is negative, in other words, it is opposed to the sense of this unit vector, it will increase the mass inside the fluid element, okay? So I forgot the minus here, sorry. Yes, thank you. So this is the first equation. This is the first equation for conservation of mass in a fluid. And as I said, this is called the continuity equation. And if you want to apply this to a general relativistic fluid, you need to change, of course, you need to write a covariant, you need to figure out a covariant formulation of this equation, which is not very difficult to do it, but I will not do it here because the Newtonian version will suffice for now. And I shall say that this is what we call the Eulerian version of the conservation equation. Okay, this is what we call the Eulerian version. When you are treating the fluid, when you are stationary with respect to the flow. You can write also using something that we call the material derivative in fluid dynamics. I will come back to this material derivative, but you can also treat the fluid from the standpoint of somebody who is moving with the fluid. Let's imagine that this was a fluid element. The Eulerian version of the equations consider an observer which is stationary, and the observer sees the fluid flowing through. And then this observer, this is a fluid element moving through. Oh my God, where is this fluid element going? If I was the observer, I would use the Eulerian version of the equation. Okay. Now, if I was an observer moving with the fluid element, now instead of being an observer that is looking at the fluid and like bye-bye, I like go with the fluid, okay, I'm moving with the fluid, I'm moving with the fluid, and everything that the fluid does, I am there, right there, witnessing everything that is happening with the fluid. Then we use this the material derivative, which is the rate of change of quantities in the fluid moving with the fluid. And this material derivative we can write like this, where V is the vector field of the fluid. And you can demonstrate, I will not do that, so this will be homework for you guys. But you can demonstrate that using the material derivative, instead of using the normal partial derivative, using this material derivative, you can write this conservation equation in a slightly different way as this. And we call this the Lagrangian formulation of the continuity equation. Okay? All right. So now we had a primer on the first conservation equation of the fluid dynamics. And you can play this game, and you can go ahead and you can derive other conservation equations for momentum. And you can apply the same reasoning in replacing mass by energy. Of course, in general relativity, mass and energy are the same, two sides of the same coin. So you have only one equation for mass energy conservation in a fluid. So we derive the first equation, the conservation of mass, playing the same game, first writing the integral form, and then using the divergence theorem to convert to a differential form. You can derive the conservation of momentum, which is really what the second equation there really is telling us is the new Newton's second law of motion applied to a continuous medium. And then you can go ahead and you can apply the same reasoning and derive the conservation of energy. And here on the lower right side, I'm writing the material derivative. Some people also call it Lagrangian derivative. So let's quickly go through the meaning of some of these equations. So the momentum conservation equation, we can rewrite it as the divergence of a tensor sigma plus some external forces. So on the right side of the equation, the first term corresponds to the internal forces happening on your fluid. The second term on the right side corresponds to external forces like gravity, like magic, like other things. So the divergence of what we call the stress tensor, which is the name we give to the tensor, the sigma, which is really a tensor, and here I'm not using the usual covariant notation because I'm doing now a Newtonian treatment. You can write a divergence of your stress tensor in terms of a combination of the pressure forces, which is the usual thing that we treat, some isotropic pressure, and also the combination of some viscous forces. So you can write a viscous stress tensor T on the right side of the second term, on the right side of the second equation. So therefore, your momentum conservation equation, which is here really a force density is a force per unit volume acting on a fluid element. It's a combination of the pressure forces, gravity, and the internal viscosity. Okay. So how do we write the stress tensor? It's really in order to characterize the internal forces happening on a fluid, you cannot simply use a vector. You need to use a tensor, which you can represent, as you know, as a matrix. And the stress tensor, it has to quantify the different forces happening in the different directions of your fluid element. Okay. So for instance, let's focus here on the yellow phase. You will consider a fluid element, and let's have a look at what's happening at the yellow phase, the yellow side of that fluid element. Okay. So here, to have a complete description of the internal dynamics of this fluid element, you need to describe the force that is transferring momentum on the direction x1. Sigma 2,1 is you characterize the force happening in this direction in the fluid element in the yellow phase. The component of the tensor sigma 2,3 it characterizes the force transferring momentum on that direction of that area, and you also need to consider a third force, which can be a contraction or expansion force acting on this direction of the yellow phase of the fluid element, okay? And you need to do the same for the other sides of this fluid element. And that's how you define the stress tensor, all the different forces acting on different directions on the different sides of the fluid element. The stress tensor has unit of energy density, in other words, pressure. It has units of, it is really some kind of generalization of the concept of pressure. And we can write the stress tensor as a combination of what we call the shear stresses. So shear stresses is suppose you have a side of your fluid element. A shear stress is a force doing this on the side of your fluid element. This is a shear stress, which is quantified by the red, the parts of the stress tensor marked in red. And the blue, the diagonal of the stress tensor, is a force doing this in the side of your fluid element, okay? So it's what we know, the normal stress that we know as pressure, okay? So So let's talk a little bit, now that we talk about some of the basic concepts behind the momentum conservation equation, let's talk about the energy equation for fluid. So the energy conservation is stating really that the rate of change in the internal energy of your fluid is a combination of things that are injecting energy in your fluid. In this case, viscous heating. It's an internal source of heating. If you have viscosity, if you have friction, you will heat your fluid, just like if you have friction in your hands, you heat your hands. But it is an internal friction, it's a viscosity. And so the conservation of energy is a balance of what is heating and what is cooling your fluid. And in this case, what could be cooling your fluid could be radiation, could be emission of electromagnetic waves, and also thermal conduction. And so we have the three conservation equations of hydrodynamics that you need to characterize a fluid. It's a thermodynamic description of the fluid, okay? It does not matter the motion of individual particles in the fluid. We are treating an ensemble of a lot of particles that constitute a continuous flow. And you have to couple these three differential equations, one scalar equation and two scalar equations and one vector equation. You need to couple that with an equation of state relating the pressure of your flow to the density of the flow. And if you have radiation, you need to describe how the radiation interacts with your fluid. In other words, an opacity description, and also what is dissipating energy and heating up the flow. In other words, a description of the viscosity. And when you have this, oh, by the way, the second equation is what we call the Navier-Stokes equation. It is probably the most important equation in hydrodynamics. It's one of the outstanding open problems in modern mathematics, okay? If you figure out how to obtain complete analytical description of the solutions of the Navier-Stokes equation, please post this paper on archive and wait for $1 million to arrive in your bank account, because you will get the Millennium Prize of Mathematics, which I think is still on. Okay, there are 7 very serious open problems in mathematics, and one of the problems is the complete description of the solutions of the second equation, the Navier-Stokes equation. Solving it numerically is not so hard, but doing it analytically from a more pure mathematical point of view is very tricky business. Not as hard as solving the Einstein's equations for dynamic spacetimes. And then you can start doing fun things once you have this arsenal of conservation equations. You can apply for jobs in the industry and be hired by BMW. And then you can model the flow of viscous air around a car, okay? And then you can help your company make a lot of money and get rich, and then donate part of your money to physics institutes around the world. Now that we have the arsenal of conservation equations for fluid dynamics, let's talk a little bit about the nature of the mechanism, which is removing angular momentum from these accretion disks around black holes. In other words, if you have an accretion disk and you have a central object, there is something removing angular momentum from the particles, decaying the orbital energy and making them flow towards the central object, releasing that energy along the way through light, through electromagnetic radiation. What is the physical mechanism responsible for removing the orbital energy of the gas? That's the question we are dealing with here now. And in order to have a conceptual picture of the physical mechanism removing angular momentum, we need to realize that black hole accretion disks or neutron star accretion disks or any kind of disk around a central object in astrophysics is really a fancier version of the Kepler's problem, of the two-body problem, okay, where you have a lot of test particles which have a negligible mass compared to the mass of the central object. And if this is the case, you can really write the angular velocity of the particles in your flow with the so-called Keplerian rotation velocity, which I believe that Ian derived yesterday, or on the I think he derived yesterday or on the first day. He derived the GR version of this equation. It's not hard to derive it in the Schwarzschild metric. And it's a coincidence that it's the same as the Newtonian Keplerian rotation, because it only is the Keplerian, the Newtonian version, the GR version and the Newtonian version, they are only the same if you use Schwarzschild coordinates. If you use different coordinates, they will not be the same. Okay, but the thing is, okay, accretion disks are a fancier version of the Keplerian rotation velocity law. So imagine that the conventional picture of fluid dynamics, suppose you have a boundary plate and you have a flow moving and sliding through this boundary plate shown in red here in this picture, okay? So one of the boundary conditions of this problem is that the flow right at the boundary will be stationary with respect to the boundary. And then you will naturally have a differential flow. The velocity at the boundary will be zero, and then it will increasingly increase as you move farther away from the boundary. Now let's replace the boundary with a black hole, and then you now have a fancier version of Kepler's problem. And you will have, you expect to have something that looks like the Keplerian differential rotation with the, well, in this case, the vector should be increasing towards the black hole, the velocity vector, rather than decreasing. My mistake, I should have corrected that. But the basic idea here is differential rotation. The velocity of the particles around the black hole, they change with radius, okay? And if you have different elements of the fluid with different velocities, they will slide through each other, and they will have viscosity, and they will dissipate energy, okay? This is hydrodynamic viscosity. So in other words, if you have something that looks like this, but in the real physical problem, again, in the real physical problem, you should have the black hole here, and then the velocity vector would be this, okay? It's in the opposite sense of what the figure is showing. So in this case, you will have shear stress, you will have viscosity, and you will have energy dissipation. So this led many theorists decades ago, once the observational discoveries were suggesting that you have generation of energy in black hole accretion disks, many theorists, they had a suspicion that hydrodynamic turbulence triggered by the shear stress in these flows could be responsible for driving accretion in the universe, okay? And nowadays, we can recreate this kind of hydrodynamic shear stress in the laboratory, something that was not possible a couple of years ago. So for instance, this is a very nice actual lab experiment in Princeton. It is called the Magnetorotational Instability experiment. You spend millions of dollars building this machine where, with the goal of investigating the nature of turbulence, actual empirical investigation of turbulence in accretion disks. And how do you do that? You fill up a cylinder with water, and you play with the rotation law of some spinning engine to try to recreate a differential rotation in some kind of fluid, which is what they are trying to do here. They have an inner cylinder and outer cylinder, and then by playing with the rotation velocities of the two cylinders, they can try to recreate this kind of velocity law, but in the lab. Okay, with the goal of answering the question, is hydrodynamic turbulence driving, removing angular momentum in astrophysical disks? But we cannot go to a black hole and throw ourselves in the black hole and investigate this in situ. So the second best thing we can do is do an experiment and investigate this in the lab. And the answer is no, a sound no. Pure hydrodynamic turbulence cannot be the mechanism responsible for removing angular momentum and allowing accretion to proceed in astrophysical disks around black holes, okay? This was a Nature paper published a couple of years ago reporting some of the results of the experiment I just showed you, and the conclusion is a sound no. If you only have hydrodynamics, you cannot really create these kinds of rich accretion disks around compact objects and drive accretion in the universe. So what is removing angular momentum in disks around compact objects in the universe? If it's not just pure hydrodynamic turbulence, what then is driving accretion? And here we now have to thank, again, the great Subrahmanyan Chandrasekhar, because he was one of the first people, together with Velikov, he was one of the first people to realize that if you have rotation, if you have differential rotation, as I said, a fancier version of the Kepler's problem, and you have magnetic fields puncturing through the disk, it will naturally expect a mechanism called magnetorotational instability to occur in your accretion disk. And then this was in 1963, so right more or less at the same time that quasars were being discovered by Martin Schmidt. Chandrasekhar published a paper on MRI instability applied to astrophysical disks. And then almost 30 years after the breakthrough of Chandrasekhar, through plasma physicists, Stephen Balbus and John Hawley, they realized, they rediscovered the magnetorotational instability and its role in accretion disks, and they published this paper, which now is one of the most cited papers in theoretical astrophysics, where they prove, they do some kind of instability analysis. They do the linear regime of the instability analysis. Okay, so they have lots of dispersion relations and linearization and perturbation theory, and they demonstrate that MRI can in fact drive accretion. In other words, if you have a differential rotation and you have a magnetic field in this direction in your disk, okay, it will naturally establish a mechanism for removing angular momentum from the particles and letting them die in the heart of darkness at the center of the accretion disk, the central object. There is a simple analogy, of course, this is a very simple analogy, it has some issues, but the simple idea is, imagine you have two fluid elements in your charged gas, and this is the metaphor here. You have two fluid elements and you have a spring connecting these fluid elements. The spring in our metaphor would be the weak magnetic field passing through the two fluid elements at slightly different radii in your disk. And what will happen as you proceed moving is that the two fluid elements, they will start oscillating, and then the red element will slowly move towards the inner radii with larger velocities. The other element will, by chance, move to a larger radii with smaller velocity. It will have an increasing oscillation strength in the spring. The metaphor of the spring is the magnetic field threading, passing through the two fluid elements. And increasingly, it will have a runaway instability where the red one will move increasingly towards the center and the blue one will move farther away. Okay, this is effectively a diffusion, okay? So, some kind of diffusion where part of the gas will lose angular momentum, and to conserve everything, part of the gas has to move away. In an actual accretion disk, the spring, it's not really a spring, is a magnetic field. It's a poloidal magnetic field, and the red and the blue elements would be, this would be the red one, and this would be the blue one. Okay, so one of them moves far away, the other one moves towards the center of the accretion disk. And the bottom line is that magnetic fields are the main agents responsible for removing angular momentum and allowing accretion to proceed in the universe. However, we can still have a simple model. We don't need to use the equations of magnetohydrodynamics to model the system. We can make a lot of progress by playing with our viscous stress tensor and add terms to your viscous stress tensor that mimic the effect of magnetorotational instability. So this is a game that you can play. You can use hydrodynamics without incorporating explicitly the magnetic fields. So let's now apply all these equations that we talked about to try to understand in a global, unified way the kinds of accretion disks we have in nature around compact objects. So one trick that we can do, in my opinion, is a very nice way of trying to make sense of the complexity of accretion disks, is you take the poloidal component of the momentum conservation equation. Poloidal meaning the component of the equation in cylindrical coordinates along the R and Z directions. Okay, this is the poloidal component. So you can write this the poloidal component of your momentum equation, and you will have several different terms addressing the different physics that is responsible for ensuring that momentum is conserved. You have an advection term. So advection is let me show you what advection is. Okay, advection is the transport of a quantity in the fluid by motion of the fluid. Okay, so imagine that we had a car here. Okay, the car is the quantity, and there was a flow passing through this lecture room. And imagine the car was transported with the flow, okay? We can say that the car is advected with the flow. Advection of the car. Here is an example of what I'm talking about. The cars are being advected with the flow, okay? This is advection. The transport of quantities by the pure motion of the flow. Of course, you would not want to be the owner of these cars. Okay, so we are all sad, right, for the owners of these cars. But this is the concept of advection. Okay, so you have an advection term, advection of a momentum. You have the term responsible for the pressure support of your flow. You have gravity, you have rotation, and you have viscosity, which also transports momentum. And it turns out that we can classify all possible solutions of accretion disks by having a very qualitative understanding of the role played by the different terms in this equation. So, if advection is not important and rotation is very low, and you don't have viscosity in your flow, these terms are negligible, so the only important terms is the pressure support and gravity. And this kind of approximations correspond to stars, okay? Stars, stellar envelopes, and stellar atmospheres they can really be modeled by this approximation to the momentum equation. And this resulting equation where you zero out all the other terms is really the equation of hydrostatic support of stars, which in general relativity is the Tolman-Oppenheimer equation, the covariant version of this equation here. Balance pressure is balancing gravity. Now, imagine you have a system with conditions where there is very slow rotation of the fluid around the central object, so rotation is negligible, And you don't have viscosity is negligible as well. So the only things that are important here is advection. So there is a very important radial velocity in your flow. Pressure is also important, and gravity is also important, as is the case always in astrophysical accretion disks. In this case, you will have the solution called the Bondi-Hoyle accretion, which is just a spherically symmetric accretion of gas onto a central object. This was the first analytical solution to an accretion flow derived in the 40s, in the 1940s, by the great Bondi. And later on, also Fred Hoyle, they collaborated in a theoretical paper in the 40s. And still people use this solution to get insights in the physics of accretion onto black holes. So it's unphysical. It's only for pedagogical purposes mainly, but it's really unphysical because accretion disks always have almost always have rotation angular momentum. It's important. So we cannot simply drop out the rotation term from the equation. Now imagine you have a system where the radial velocity is very small, so the advection term is not important. And imagine that the pressure support is not important as well. So in that case, you will have a solution of the thin accretion disks, which are almost Keplerian rotation velocity for these accretion disks. It cannot be perfectly Keplerian, otherwise you would not have accretion. You will not have inflow of particles towards the black hole. And finally, if you have a system which is so complex that you cannot really drop out any of the terms in the momentum conservation equation, in that case, where everything is important, advection is important, pressure support is important, gravity is important, rotation and viscosity, everything is important. In that case, you are basically doomed. Good luck to you. And this kind of accretion disks we call radiatively inefficient accretion flows. I will talk about the astrophysical importance of each of these solutions in this lecture and the next lecture. And we call this kind of complex solution, we call them RIAFs, radiatively inefficient accretion flows. The RIAF solution was only, so each of the papers describing each of these three solutions to the accretion disk, accretion flow problem, because not necessarily have a nice disk, a nice blue ray of gas. Each of the papers describing the discovery of these different solutions is widely cited in theoretical astrophysics nowadays. The thin accretion disk solution was discovered in the early 1970s by two Russian astrophysicists, Shakura and Sunayev, and it's one of the most cited papers in theoretical astrophysics. The RIAF solution, where the disk has this kind of funny shape, the size of a donut, more or less. So you look at this and you get hungry because it looks like a donut, maybe, or maybe not. No, I don't know. The RIAF solution was discovered only in the early 90s, so 20 years after the thin accretion disk solution was discovered. Okay, so each of these solutions is very important to make sense of observations of electromagnetic radiation from black holes, from astrophysical black holes. And now I will try to make a unified theory of what connects all these solutions together. Okay, is there one single parameter that we can use to try to connect? By varying this parameter, we go through the different solutions. Can we make a unified theory of accretion disks around black holes? And before we talk about the unified theory of black hole accretion disks, we need to talk about some preliminaries. And we need to talk about the important concept of Eddington luminosity before we proceed. Has anybody here heard about this concept of Eddington luminosity? Who has not heard of the Eddington luminosity? Can you raise your hands? So more or less 70% of the classroom. So the people that didn't raise your arms, you heard and you studied Eddington luminosity. That's a fair assumption. Okay. So for those that probably have an astronomy, astrophysics background, they heard about the Eddington luminosity. Those that did not hear, this is important to make sense of black hole accretion. The Eddington luminosity is an important concept because it teaches us what are the limits to how much you can feed a black hole in nature. So the idea here is the following. It's a very general concept, the concept of Eddington luminosity. Imagine you have a central object with a mass m, okay? If this central object can be a star, can be a planet, can be anything. But let's imagine that this central system here with a mass m is radiating photons. And you can quantify the power radiated by these photons through an isotropic flow of radiation pressure quantified in terms of a luminosity, an electromagnetic luminosity. Okay, the only color I have is yellow and white, but that's okay. I think there are more colors, right? No. These theoretical physicists and their limited choice of colors. No, it's okay, Ricardo. It's okay. It's not really important. I don't know why I care about this. But imagine, okay, so you have some flow of radiation coming from the central object. And let's imagine that you are trying to feed the central object with a spherically symmetric shell of ionized gas. So it's spherically symmetric, okay? It's fully ionized gas, okay? And let's imagine that it's mainly ionized hydrogen, okay? Just for the sake of the argument, it's mostly ionized hydrogen. In other words, electrons and protons. Ricardo, don't worry. For future reference. Don't worry. Okay. I already figured that. Great, thank you. Okay, so you're trying to feed the central object with a spherically symmetric shell of ionized hydrogen, and the central object is irradiating radiation. Okay, so what are the forces on one element of this flow of ionized gas? Okay, the first force that is acting here, of course, is gravity. The force of gravity is pulling this layer, this element towards the central object. But you also have an opposite force, which is because photons are transferring momentum to the gas, Thomson scattering, okay? So we can write an effective radiation pressure force, which we call F rad, okay? So how can we write the radiation pressure? The radiation pressure is, of course, the radiation pressure force divided by the area on which the photons are transferring momentum. Okay. From the way we understand radiation, the transfer of momentum by radiation, you can write this as F, which is the flux of radiation, divided by C. Okay, this is how you quantify and you characterize momentum transfer in a relativistic gas. In this case, the gas is made out of photons. All right. So the force, okay, perhaps my choice of notation is a bit poor, but F here is flux, and F rad is the radiation pressure force. So the radiation pressure force will be the area times the flux divided by C, okay? So the area, the thing is, we can think that the photons are interacting strongly, scattering electrons, transferring momentum to the electrons, okay? So the relevant area that we have to put here is the effective area, the classical area associated with the electron, the Thomson cross-section, okay? Divided by C, times the flux of radiation will be the luminosity divided by 4 pi r squared, where we are considering that the distance here is r. And that's it. That's great. We just wrote down an expression for the radiation pressure force acting on that fluid. Well, the gravity force is very simple. We just write Gm m r squared, okay? Where this is the central mass and this is the mass of the particles on which are suffering gravity here. Now, there is a very interesting catch here when we write the gravitational force. The particles that are getting the momentum transfer from radiation will be electrons because they are less massive, they are 1,000 times less massive than protons. So they are the ones getting the bulk of the momentum from photons. However, the particles that are really more strongly suffering the gravitational force will be, of course, the protons. And protons and electrons, they have the electrostatic Coulomb force, okay? So if you do something to the electron, okay, imagine here, I have an electron here, and I have let's take a different color. Electron and proton, okay? And they are all falling towards the center. So gravity, I said this is the electron, this is the proton, okay? So gravity, this guy will feel more strongly because the inertia of the proton is higher, okay? So the proton is like, oh my God, gravity! But they are interacting through a Coulomb force here, right? So they are connected more or less. However, the electron is feeling the radiation pressure, like, oh my God, photons, oh wow, what's happening, okay? So they are connected, and this is a tug of war here, okay? Gravity affecting mostly the protons, and radiation pressure affecting mostly the electrons, okay? And they are connected in a tug of war here. Whatever one does, it pulls the other together by the Coulomb force, which is way stronger locally than the gravitational force. So they are effectively connected. So here we will write the mass of an ionized, because they are connected by Coulomb, we put here the mass of the electron and the mass of the proton. Of course, the mass of the proton is much bigger than the mass of the electron, so we approximate this as this. Very good. So the question we want to answer is, okay, you are feeding this central system with gas. What will be the luminosity if you crank up the luminosity? What would be the luminosity at which the radiation pressure would equal gravity and stop the accretion of this shell? Okay. Whoa! Too late, my friend. Thank you very much. Thank you very much. So what is the limiting? Now I have more colors. I can express myself with more ideas. Not really, but let's continue. Okay, so what is the limiting luminosity at which if you crank up the luminosity, the radiation pressure is so strong that it counterbalances gravity and stops accretion of this shell of matter, okay? So you can answer this question by equating gravity with the radiation force. equate here, r squared drops out. So we are interested, of course, in the limiting luminosity at which accretion would stop. And this limiting luminosity is simply Gm, capital M, mass of the proton times C divided by the Thomson cross section, okay? So this is what we call the Eddington luminosity, okay? It's the Eddington luminosity because if the central system was shining with this amount of luminosity, it would stop accretion and accretion would stop. And this is a very important concept to make sense of accretion disks, okay? The Eddington luminosity. It's the maximum luminosity that an accretion disk could have. Okay, if the energy being radiated by the accretion disk gets comparable to the Eddington luminosity of the system, the accretion disk will get stuck and be destroyed. If it exceeds the Eddington luminosity, it's not accretion anymore, and the disk will be destroyed. Okay, it's a very useful unit. So another thing that's very useful, and my time is running out. But another thing that is very useful that I would like to talk about before we go, and we will see this quite a lot now, the concept that we call the Eddington ratio, which is simply expressing the in terms of the Eddington luminosity, okay? This ratio, which is a dimensionless ratio, we call it the Eddington ratio. And of course, for an astrophysical system, if lambda is close to 1, then accretion stops, okay? Oh, but by the way, if you want to put a more convenient way of writing the Eddington luminosity for astrophysical purposes, you can plug in your favorite numbers here and express m in terms of solar mass and use the terrible units that astronomers like to use, CGS, and write for one solar mass central object, the Eddington luminosity is 10 to the 38 ergs per second. So the Eddington ratio for typical astrophysical systems is usually less than 1, otherwise accretion would stop. And finally, you can also define something called the Eddington accretion rate. So the Eddington accretion rate is it's very simple, is you write your accretion rate of your system using that engineering point of view. The accretion rate is the luminosity of your system divided by the efficiency of converting matter, rest mass, energy of matter into radiation. What you simply do here is that if this is the Eddington luminosity here, then the accretion rate is defined as the Eddington accretion rate. And if you plug in the typical numbers, if you put a more convenient numbers here that you can apply directly to astrophysical systems, and you express your mass here, let's say we write this for a supermassive black hole, and we put a standard of comparison of an efficiency of 10%. The Eddington accretion rate, the accretion rate in the system that we would produce at an efficiency of 10%, and Eddington luminosity would be 3 solar masses per year. So this is the definition of Eddington luminosity. This is the definition of Eddington ratio, and now tracing back to the important concept of Eddington luminosity, which is important to parameterize accretion disks in the universe. Well, to finish the lecture now, let's just lay out the basic picture of trying to do an unified theory of accretion disks. How is my time?
Okay, it should end 5 minutes before because we have the clockman too, so we need to have 1 hour.
So when is 5 minutes before?
In 3 minutes.
In 3 minutes, okay. Okay, so tomorrow we will, before tomorrow, let's write the energy conservation equation in a more compact version, which is this, where S is the entropy of the gas, T is the capital T is the temperature. And so we can write the energy conservation law in terms of equating the rate of increase of the entropy per volume of the gas is a balance of what is heating your gas and what is cooling your gas. So heating minus cooling is what remains in your gas, and this must go somewhere, so it is advected. It's advected with the flow, if advection is important. The term key ADV. So key is the cooling or heating rate. Okay, advection is a form of cooling. So heat energy must go somewhere. So you can write your energy equation in a very compact and conceptually simple form, where heat, the key plus, equates the cooling, key minus. So Q minus is the radiative cooling and the advective cooling. So if you have a fixed fluid element, you can cool it by releasing radiation or by just removing the heat by advection and taking it out of a fixed volume element. And by using these concepts now, we can have a simple description we can unify and write a unified theory of accretion disks, where we describe an accretion disk with just the accretion rate scaled through the Eddington accretion rate. And let's now pay attention to what happens with the thickness of the accretion disk as we change the accretion rate here. And we will discuss this tomorrow and have this unified field theory of accretion disks in the universe tomorrow. Thank you very much.
We have the clockman too, so we should have 1 hour for lunch. Just one quick question, if you want. Okay, let's go for lunch and be sure to be back a few minutes before 2.
Precisamos conversar.